This is a demonstration of Newellian coordinates and point Q representation. Eulerian and Lagrangian are the two most used coordinate systems for describing the traffic state. The Eulerian coordinates split the spatial temporal space into grids, where the traffic state is defined as the density in each grid. At each time step, the dimensionality of the Eulerian traffic state equals the number of grids. Lagrangian coordinates keep track of each individual trajectory's movement. For each time t prime, the traffic state is represented by the location of each trajectory k. The dimensionality of the Lagrangian representation equals the number of trajectories at each time step. However, both Eulerian and Lagrangian representations have certain limitations. In this paper, we propose the so-called Newellian coordinates, which enable us to use a point Q representation. The Newellian coordinates are established based on the assumption that all vehicles follow Newell's car-following model and only have free flow and stop states. Instead of using time-space t prime and s prime, the Newellian coordinates define new time and space coordinates. Under the Newellian coordinates, the horizontal time axis is defined as the free flow arrival time t, which is parameterized by the free flow speed vf. The vertical space axis is defined as the unit traffic flow n, which is parameterized by jam space headway h. The equations in the box show the mapping between the time space t prime s prime and the Newellian coordinates tn. The vehicle trajectories can be converted to a point Q under the Newellian coordinates. As a result, the traffic state representation is the Q length xnt, where the dimensionality is 1 at each time step. Now, we focus on the Newellian coordinates and see how the vehicle trajectories can be projected to a point Q process. As aforementioned, with given free flow speed and jam space headway, the Newellian coordinates are defined over the free flow arrival time t and unit flow n. Given the traffic signal state, the dashed black line is the departure shockwave. Assuming there is a new vehicle arrival at time step 1, the blue line represents the trajectory following Newell's car-following model. The right-hand side table shows how we can convert vehicle trajectories to a point Q representation. AT denotes the number of arrivals at each time step. In this case, it equals 1. XNT denotes the Q length. In this case, XNT is also 1. XT is defined as the number of stopped vehicles at each time step, which can be counted starting from the departure shockwave. It is easy to verify that the relationship between XT and XNT is given by these equations, which means that XT is equal to XNT minus the elapsed time from the end of the red time TR when XN is greater than 0. In this case, TR equals to 1, and XT and XNT are equivalent. BT is the number of departures at each time step, where a departure occurs when a vehicle leaves the intersection. We can see from the figure that there is no departure at time step 1, and 1 departure at time step 2. Now, we move to time step 2, and there is another new vehicle, and the arrival AT will be 1. Q length XNT is 2. The number of stopped vehicles is 1. And the departure at time step 3 is 1. Now we move to time step 3 and assume that there is no vehicle arrival. Arrival AT will be 0. The Q will be cleaned up, and both XNT and XT will be 0. As time continues, we can keep updating the right-hand side table according to the vehicle trajectories. Time step 4. Time step 5. Time step 6. Time step 7. It is easy to check that the dynamic equation of xt is given below. which means that for each time step, xt equals xt minus 1 plus the arrival at minus the departure bt. We call xt a point q since it does not contain any spatial information. It behaves as if all stopped vehicles are stacked at a single location. In this way, we have converted the vehicle trajectories to a point q process under Newellian coordinates. The next video will extend this point q process to a stochastic setting and utilize the newly proposed probabilistic time-space diagram to project it back to the spatial temporal space.